Hello everyone. Welcome to my channel Economics by Dipankar. So in today's video, we are going to discuss about growth models. And we have seen that many of the questions are being asked from growth models, especially सोलो मॉडल. तो आज के इस वीडियो में हम लोग सोलो मॉडल के बारे में ही विल बी डिस्कसिंग इन डिटेल्स. And apart from that, we will also be discussing like what kind of questions are being asked and how to solve those questions. So, solo model in itself is a big topic. We might not be able to complete the entire thing in a single video. So, what we can do is that we'll try to complete as many number of different topics which are important under solo model, solo under solo model, and we'll be also be discussing how questions are being raised and how to solve those questions. So all those students who are preparing for either entrance examination or UGC NET exam for economics, please watch this video. We are going to discuss in details, and this might help in solving all your queries regarding solo model. And if you have not subscribed the channel till now, so please subscribe so that you can get all the latest updates. And also press the notification bells to receive all the important updates. So, solo model this began late in 1950s, and why solo model is important? Because for two reasons. One, this is the first model we talked about convergence. Like irrespective of what is the the growth rate of the economy, if all the fundamentals are similar, both the economy will converge to a particular level. The second reason is that Solow was the first person to use classical growth models. Like he used a Cobb-Douglas production function of, let's say, y is equal to for A, K, alpha, and L, beta, where alpha and beta were the, you can say, share or whatever, and K is your capital and L is your labor. So after Solo, there were many changes which were introduced in, let's say, the equation, and how there was a steady state rate, again the golden consumption level. So we are going to go through all those things. And secondly, there are many important variables, like if there is a growth rate in saving rate, then how the economy is going to change. So if S increases, what will happen? If there is a constant growth in the population of working labor, so how it is going to change? If there is a growth rate of A, that is the technological progress, so how it is going to affect your K, that is a steady state level of capital. Okay, so for discussion we are referring to the book by Gregory Mankiw and chapter 7. So, among all the many books which we have referred for this particular topic, we felt that yes, chapter 7 of Gregory Mankiw, Macroeconomics, is the best suitable book. And even if you want to read a solo model, so we will recommend chapter 7. Okay. So, solo growth model, and we'll be discussing. So, what we are going to do is that this is your the book part, and here we are going to write all the important things that we are going to discuss. So solo model. Okay, and we will be using simple production function, or you can say y is equal to, for the beginning, k alpha l beta. And if you don't know about the property of Cobb-Douglas production function, then you must understand what are the different variables, and what are the important, you can say, relationships with, like when K, alpha, and L is 1 minus alpha. So what does this signify? If alpha plus beta is equal to 1, what does this mean? If alpha plus beta is greater than 1, what does this mean? If alpha plus beta is less than 1, what does this mean? Because all the three have different interpretations, and we'll be dealing this topic separately. we'll be taking one different session regarding coop dollars production function, and if there is a transformation, what does that mean, and how are we going to interpret the coop dollars production function? Because many times we have seen that even in the case of entrance examination and UGC papers, they'll give you a production function, especially in the form of a coop dollars production function, and they'll ask, like they will give a transformation of coop dollars production function, and then they will ask which is the exact transformation. So we are going to see to that also. So supply and demand. Yeah. So the first thing that Solo says is a production function, and it has only two variables. See, production function which was implied by Solo had only two variable. One was capital, and the second was labor. So these were the input variables. Input variables. Okay. Now, you can see when we say output produced per unit of flavor. So when, let's say, y is equal to k, or you can say y is a function of k, which is capital and labor. So y by L is output per unit of labor. Okay. So see, the relationship is different from if we say delta y by delta y L. So here is output per unit of labor, and when we write in terms of delta y by delta L, where delta is your change, so this is change per unit of output divided by change per unit of labor. So this is, you can say, in terms of growth rate. So that's what I told you. There are different symbols and different interpretations. So we must understand the function of amount of capital per worker. So similarly, when we write Y by L, so it is your output per labor, and when we write K by L, it is capital per worker. Capital per worker. So this is simple ratio, nothing more. And MPK is marginal product of capital. Marginal product of capital. So what happens is like so what happens now? Let me start the solo model. Okay. So let's say our production function is y, where y is your output. Output is a function of, let's say, f, capital and labor. K is equal to capital and L is equal to labor. So in terms of output per unit of labor, we can write y by L is equal to f K by L, comma 1. So this is your output per unit of labor, and this is your capital per labor. Okay. So for y by L, we can write it as small y. So y is equal to, this becomes smaller, and it is k. So your f is equal to this k by L. Okay, and your k is equal to capital K by L. Okay, so this is the simple thing, nothing serious over here. So what is happening is that we define in terms of, let's say, capital per worker. Okay, let's say the production function, the slope of this production function shows how much extra output a worker produces when a given unit of extra capital. This amounts to the marginal product of capital. Okay, the marginal product of capital. So let's look at the production function. This is output per worker and this is capital per worker. So what does this slope at any given point, or at any given line, what does this slope denote? The slope says what is the marginal product of capital, MPK. Okay. So, and how do we interpret marginal product of capital? The slope of production function is the marginal product of capital. If K increases by 1 unit, Y increases by MPK units. That means, uh, like when we say, like, if you want to increase the capital, let's say the capital is 10, now you have increased to 11. So, what is the change in Y? This change in Y is donated by MPK. Okay. The production function becomes flatter as K increases, inducing diminished marginal product of capital. And why this becomes more in terms of, let's say, flatter and flatter, at a point if we extend it, this might become this like a horizontal straight line. This shows that at any given point of time, if you keep on increasing capital without increasing labor, then there is diminishing marginal returns. Diminishing marginal returns means, if you keep on, like, there are two variables, two factors of production, labor and capital. But then if you keep on just increasing capital, then there might be some unit changes in your output, but the change in output will keep on decreasing. At the initial level, when your let's say in terms of production function, when your product is, let's say, capital is 10 and your labor is 10, and let's say each unit of labor uses 1 unit of capital, then this means your if you changes from 10 to 11, or if you keep on increasing 11, 12, sorry. So what happens is that for the same unit of labor, there is extra capital which goes unutilized. And that's why we see in terms of, and how do we measure that? We measure in terms of diminishing marginal returns. And that's why this diminishing marginal returns is negative. Okay. Demand for good and consumption. So this is simple, we have seen in macroeconomics also. Y is equal to C plus I, where C is your consumption, I is your investment. And how do we say now, if we introduce S is equal to saving rate. So this is pre-worker version of the national income accounts identity for an economy. Okay. And people save, and S for their income, and their fraction, consume a fraction of 1 minus S. What does 1 minus S show? 1 minus S says, like, in terms of production function, or even if we say in terms of national income, let's say Y is equal to C plus I. Okay. Where I is equal to investment. So what is this unit of investment? Unit of investment is equal to SY. Why? S is your saving rate. And this saving turns into investment, because there is a simple assumption, like, whatever we save is equivalent to your investment. Like if we save rupees 10, then we are going to invest rupees 10. Okay. So we can write C plus, in terms of I, we can write S Y. Why S Y? Because S is the saving rate and Y is your economy. You can say the output of the economy. And this is your investment. This is in terms of total investment. So if we replace Y is equal to C plus SY, so this goes This side C is equal to y minus sy, or C is equal to 1 minus sy. So this is how we are going to get the equation. So what does this say? Is a saving rate is a number between 0 and 1. 0 means no saving, and 1 means no consumption. No means no. 1 means no consumption. That means that whatever the economy is producing, it's there is no consumption by the economy, and the whole production or the whole output goes into reinvestment. Okay. To see what this consumption function implies for investment, substitute. So again, we are going to substitute this in terms of. So this is what we are going to get. What I had written over here. So I had written S Y. So it's the same thing. Okay. So now we'll start with growth in capital stock and steady state, and we'll have to define what do we mean by steady state. Steady state. And what happens to the variable k, what happens to the variable c, what happens to the variable s. So we'll look into it. So there are many important, you can say, variables which have been introduced in Solow model, and one such variable is depreciation. Depreciation means there is wear and tear in the capital that is being used in the production or used in the economy. So this means that if there is a 10 unit of capital in the economy, and next year in T1 period, so if this there is, if we write, let's say T naught, T1, T2, where this is year, starting year after 1 year, after 2 years, and there is a, let's say, 10 unit of capital. So if next year without any additional capital, if the remaining capital is, let's say, 9, so what we say is depreciation is equal to 10%. This means 10% of the capital gets torn away. Again, it will be in T2 period, it will be 8 units. So this is an important concept which have been introduced in terms of depreciation. And again, I is equal to S as a function of K. Why as a function of K? Because we have seen Y is equal to Fk, right? So Sy is your investment. So we say that I is equal to Sfk. So this is an important thing that we must remember. So this is your, in terms of, if we talk about, this is in terms of your economy, and I is equal, if I is your investment, so investment is saving rate into your Y, because we have seen I is equal to Sy. So for this Y we have written in terms of production function. Got it? So now you need to understand this graph. What does this graph show? This is your output, okay, and this is your investment. So this says that at any given point of time, your investment is going to be less than output. Why? Because we know F K is equal to C plus I, where C is your consumption, and I is your investment. So C is, so we can say C is equal to Fk minus I, or in place of I we can also write C is equal to Fk minus S F K. We must keep in mind that we have to use small k. So C is equal to 1 minus S F K. Okay. So what does this mean? This is your investment line. This is your total output line. So at any given point of time, the difference is your investment. This is your investment, and this is your consumption. So this is the difference. This is your, if we talk in terms of, if we talk in terms of, let's say this, so the equation for this we can write C is equal to 1 minus S F K, where this S is your saving rate. See, important thing to understand is that why this is less than FK. Why SFK is less than FK? Because we have seen earlier that S is less than 1. If there was a case where S is equal to 1, so there would have been no difference between this line and this line. So you can say that your S determines whether your consumption in the economy is higher or lower. If we term this as S star, and we make a separate line, let's say like this, and this is your S1 star, where S1 star is greater than S star. So in that case, if this is the situation, then your C1 star will be less than C star. Why? Because this is your consumption, and at any given point, this is your investment. So you have seen how the consumption in an economy depends upon the saving rate of the economy. Saving rate, because saving rate determines your amount of production or amount of output which gets reinvested in the economy. Okay. Now there is a different concept that we discussed earlier, that was depreciation rate. We talked about depreciation. What is depreciation? Depreciation is amount of capital which gets out of the economy. Now, depreciation rate is the rate at which the capital gets removed from the economy. Okay, so we said it was 10%. This means every year, if the capital doesn't get reinvestment, or there is no extra unit of capital added each year, then in that case, an economy will get out, or any capital investment, there will be no capital after 10 years. So this is all that we need to understand. Okay. So again, change in capital stock. Depreciation is your change in capital stock, which is investment minus depreciation, or we can say capital K. That is, capital K is your actual rate or the change in capital. Okay. So K is your total capital, and delta K is your change in capital. Got it? So now we need to understand this. So when this is your rate of depreciation rate, so let's say a depreciation rate is 10%, okay, 10%, and if your capital stock is 10, this means 0. So this is 0.1 into 10 is equal to 1. So 1 unit of capital will get removed of the economy if the total unit, that is 10, remains constant. So now we need to incorporate this equation into the equation, this equation. So we need to remove this. So we have already seen I is equal to S F K, and substitute this. So this is your delta K. So here what we need to do, so this is your equation 1. Okay, this is equation one. And when delta is the rate at which the capital depreciates, this means rate at which the capital depreciates. So delta K is change in capital. Change in capital is equal to actual unit of capital minus delta K. Delta K is what is the reduction? Reduction due to depreciation. Okay. So this is your change in capital is equal to actual capital stock minus depreciation. So what we can do is we can write delta K is equal to S Fk minus delta K. Why Sk? Because we know from this one, okay, saving rate into total output is your investment. So this is an important equation. This is an important equation. Why important? Now we can see. So what does this equation show? There is a relationship between investment and depreciation. And what depreciation? Like we want to reach to a point where there is no change in capital stock. No, no change in capital stock. And when there is no change in capital stock, we say that we have reached the steady state level of capital. Okay. So this is your depreciation line. If delta is higher, then we'll get a curve like this. When delta is lower, we'll get a curve. Okay. So a constant fraction of capital stock wears out every year. Depreciation is therefore the proportion to the capital stock. Okay. Now we need to look at this line. Okay. And now let's say that we have also this is your F K. Okay. Let's make this point. So why do we call it a steady state? A steady state is a point where change in capital stock is zero. So what does this mean? This means that the rate of, the rate at which the capital is getting out of the economy is equivalent to the amount of capital that we put in the economy each and every year, so that we, balance out the depreciation. And this is what we call the K, or the steady state of capital per worker. And look what happens over here. Let's look at this point. Over here, the amount of capital which is being invested in here is greater than the depreciation rate. So what we can say is that we can keep on increasing, or we can keep on adding capital. Now here what happens is your depreciation rate is higher than the capital induced each year. This means at point this one, if the capital investment is, let's say, each year that is 10 and depreciation is 12, the total depreciation which take place is 12. So we want to come down. Over here, the capital investment is, let's say, 5, but then the depreciation is only 4. So we can say, okay, no, we can keep on adding more capital, because we want to reach to a point where change in capital is constant, and that constant is equal to 0, because we want to reach to a point where there is no change in capital. This means that the amount of capital that we induce each year is equivalent to the amount that gets wear or torn out. It doesn't mean that we don't want to or we are not going to induce new capital. We are going to induce new capital. And what is the amount of capital that we are going to induce each year is your K star. Okay. So it says, and this is one of the most important, you can say, contribution of Solo model. That is, regardless of the level of capital with which the economy begins, it ends up with the steady state level of capital. And since the steady state represent the long run equilibrium of the economy, this represent the long run equilibrium of the economy. So let's see. So this shows that there is a single capital stock. There is no other point in the whole range where you will get different K star. Okay. So this is a single point where your K star, where delta K is equal to zero. There is no other point. So single capital stock. Single capital stock means it is there's just single amount of capital, the single amount of capital at which the depreciation rate is equivalent to, you can say, new capital induced. So, and which we say that a change in capital stock is zero. Change in capital stock per labor is zero. Okay. To see why economy always ends up, suppose the economy start with less steady state capital in such a K1 in the figure, in this the investment exceeds amount of depreciation over time. The capital will keep on rising. Approaching to the steady state, so this is again a numerical problem. You can go through it, and what happens is, like we have seen. So the equation was delta K is equal to F or S F K minus delta K. This was the equation. Now when we put this at zero, this becomes S F K star is equal to delta K star. So this is, you can say, that unit of capital at which total investment in the economy is equivalent to the depreciation rate. So this is how we get the equation. And you can further keep on solving these equations like SFK star is equal to delta K star, So you can get a K star is equal to SFK star by delta. So again, this says how do we get the steady state level of capital? Steady state level of capital. So this is the equation to get the steady state level of capital. And the same has been shown, it has been solved over here. So your different values which you get, and then you put in the value, and how do you calculate all those things? So it has been shown over here. Or we calculated as, let's say, K star is equal to S F K star by delta. This is your depreciation. So K star by F K star is equal to S by delta. So this is the same thing. Okay. It's more like when you want to solve these equations. So this is a very good example to solve the equations. And many times we have seen that, especially in the entrance examinations, you might get such questions like how to solve. Okay. And in terms of like how to get this delta K, and again, if you have received all the values, so it's very easy to calculate. It's not a big deal. Okay. Now the next thing, see, so why this is important? Why this is important? So the question that usually that we get in the exam is, we have seen this K star is equal to S F by delta. So the question that is usually given is that if S is increased, how do we interpret this? What happens? Or if delta increases, what happens? What happens? So simple, like if you want to visualize, so this is your, let's say, this is your delta K, and this is your SFK, okay? And this is steady state. Now, what happens in case of when your S increases? So there is a increase, or you can say there is a shift in this SFK, where this is star. S star is greater than S. So there is a upward shift. So when there is a upward shift, so this is the new steady state. New steady state. So there's a increase in capital investment in the economy. And of course, when there's an increase in capital investment in the economy, the output will also increase. Why? Now, why this will happen? Because in case this is your, let's say, F A, and earlier it was this much, and now it's this much. Okay. So we say, okay, sorry. We say this is level of your new output. So even Fk star new one will be greater than, let's say, f not k star. So as the k increases, so as your s increases, your steady state capital also increases, and Fk, that is output in the economy, also increases. So I hope you have understood this. Okay. And this is the same thing which have been increased, shown here graphically. An increase in saving increases the rate of investment, and let's say from it was K1 star to it changed to K2 star. So there is a change or increase in capital per worker. So again, this is very important. An increase in the saving rate implies that the amount of investment for a given capital stock is higher. Therefore, shifts the saving function upward. At the initial steady state K1 star, investment now exceeds depreciation. The capital stock rises until the economy reaches a new steady state. Okay. So again, this statement is very important. So Solow model shows that a saving rate is a key determinant of the saving rate is a key determinant of the steady state capital stock. Okay, this is very important. If the saving rate is high, the economy will have a large capital stock and high level of output in the steady state. If saving rate is low, the economy will have a small capital stock and low level of output in the steady state. This conclusion relies on many discussions, fiscal policy. You can ignore those things. So again, we can say that saving rate has important implication on the growth rate of the economy. So the next target can also be, how do we find the growth rate of the economy, and what is the relationship between, let's say, delta S and delta Y, or what is the relationship between, let's say, S and delta Y. Delta Y is your change in capital stock, growth rate, whatever. Okay. So policies have steady state, have a growth effect, income effect, and this is something that we need to see. So before going into those impact on growth rate, and now it's important to understand the golden rule level of capital. Golden rule is regarding your consumption. See, we have discussed, like, if we again, let's say this is delta k, this is your S F K, and if this is your, let's say, F K, this is your. So we have seen at steady state, this is your investment and this is your consumption. See, this is your I. So the question is, at steady state, is consumption maximum? So this is the question, because see, one of the objective in any policy making is to maximize the consumption, maximize consumption. So our next target is to identify a point where consumption is maximum, consumption is max, and from this point or at this level of capital, what is the relationship between this k star and golden level or whatever, and we can see it might come over here, so we need to identify this optimal, and we call it optimal amount of capital accumulation from the standpoint of economic well-being. Okay, comparing the steady state. So the steady state value of k that maximizes consumption is called golden rule level of capital, and is denoted by k star gold. And Edmund Phelps made this important contribution in this golden rule level of capital, and he was awarded Nobel Prize in economics for this theory. Okay, so again, this is something that we have seen. Okay, so simply what has happened is that we have simply substituted the different values, and in place of I, why we have written this, because we can write in terms of, let's say, as Fk, or we can write delta k. Why? Because at steady state, both are the same thing. Okay. We have already seen that at a steady state, Sf k star is equivalent to your delta k star. So we can write either this or we can write either this. So this is what has happened. And this is, according to the equation, steady state consumption is what's left of a steady state output after paying for steady state depreciation. So delta K star, this is total amount of capital which is depreciated. Depreciated. Okay. So this says that whatever consumption that we are going to have is whatever is left after depreciation. Okay. So now this is your point where it is K star. Okay. This is your K star. And this is your K gold star. Now this K gold star is not your steady state. It's not your steady state. So what happens is that this line is drawn parallel to your depreciation line. Okay. And at depreciation line where the point is tangent, we say it as K gold star. Okay. So the economy output is used for consumption in steady state investment equal depreciation. Therefore, steady state consumption is the difference between output and the depreciation delta. Steady consumption is maximized at golden rule steady state. The golden rule steady state is dominated by K star gold, and the golden rule of consumption is dominated by C gold. Okay. Now, how do we interpret this? Again, interpretation is important. When comparing, we must keep in mind the higher level of capital affect both output and depreciation. If the capital stock is below K star, that is golden rule level, an increase in capital stock raises output more than depreciation, so consumption rises. An increase in the capital stock raises output more than the depreciation, so consumption rises. In this case, the production function is steeper than K, so the gap between these two curves, which equal consumption, grows as K star rises. By contrast, if the capital stock is above the golden rule level, an increase in capital stock reduces consumption because increase in capital output is smaller than the increase in depreciation. So we need to understand these two topics differently. What does this say? That at golden above golden level, depreciation is lower. Depreciation is lower than change in capital. That means this value D, sorry, delta K is less than SFK, but the change that is being introduced in this is less than what can happen in terms of your FK. That's why the increase in capital stock is taking place, but then the increase or change in capital stock is not equivalent to the change in output. Therefore, even though your output is increasing, but the change in consumption is not increasing. So, what does this say? Again, let me try to discuss with in terms of this graph. So at this point, this is your K star, this is your K star. So at let's say what is happening over here, what is happening over here? It says that your output, or it says that your steady state output is increasing. Okay, but then the change in terms of, if we also let's say capital stock, or let's draw this. It says that there are two different points. Okay, this is your in terms of SFK, this is your delta K. At this point, your SFK is greater than delta. Therefore, the changes which is taking place, if you keep on increasing SF, it will increase, but then the respective change in FK is lower than the change in SFK. Therefore, your consumption will increase, but then it will not be at the maximum point. So this is what has been explained over here. Okay, the gap between two star, which equal to consumption, grows as K star increases. By contrast, if capital stock is above the golden rule level, an increase in capital stock reduces consumption because increase in output is smaller than the increase in depreciation. Okay. So marginal product of capital. Now we can derive simple condition that characterizes the golden level of consumption. Recall that the slope of production function is the marginal product of the slope of delta k is delta. Because these slopes are equal at this, the golden rule describes that the marginal product of capital must be equal to your depreciation rate. So, what this is an important condition that at the golden rule level of capital, the marginal product of capital is equal to the depreciation rate. So, the question can be asked on this very line. They'll say at the golden level, marginal product of capital is less than the depreciation rate, equal to the depreciation rate, greater than the depreciation rate. Okay. So, this is something is which is very important. The marginal product net of depreciation equals zero. As we see, policymaker can use this condition. Okay, so this is your this has been explained graphically. Your this is your S gold. Okay, S gold means even in terms of your actual saving rate, saving rate. Saving rate in the golden rule, there is only one saving rate that produces the golden rule level of capital K gold. Any change in saving rate would shift SK curve and would move the economy to a steady state with lower level of consumption. So what does this mean is that your steady state doesn't denote your your steady state doesn't mean that at the steady state your consumption is also maximum. So the question is how to find the steady state. This is your delta A. Let's say we have this and we have this. So we can say at this is the rate. Okay. Now again, let's say we have the same line. We have this and we have this. So if your steady state is K star and this is the level of consumption K gold, why if we say that this is maximizing over here? But in case of this, if we say that it is maximizing over here at this point, so in this case, K star is equal to K gold star. But in this case, K gold star is less than K star. Okay. And how does this depend whether K gold star is equal to K star? It all depends upon your S star. That is saving rate at the economy at which your consumption is maximum. Okay. Now, again, numerical example. This is very important numerical example, and you must solve this. You must go into and try to understand how these are being solved. The transition to the golden state, starting with too much of capital. So, we first consider a case in which the economy begins at a steady state with more capital than would have been at the golden rule steady state. So, if your capital is higher, so what happens? So, your output will decrease. Okay, and this says the saving rate is reduced. Starting with too little capital, so it will take time to reach to the golden level. Now the next thing which have been introduced is your uh, population growth rate. So till now we had kept n is equal to 0. Now if there is a change in population, so how do we incorporate? So this is something which we are going to discuss again in next class. So in this class we have seen, so in this video we have seen how do we get a steady state and how do we get this golden rule level of capital, golden rule level of let's say saving rate at which your consumption is maximum, and also your K gold star is equivalent to the K gold. So I assume this video has been very much helpful for you. So please like the video and subscribe the channel if you have not subscribed till now. And if you have any query, you can write to us or WhatsApp us on 844 488 78849. So we wish you thank you and all the best.